Hello, welcome to Digital Electronics IEEE 301. So my name is ASM Nasir. The course objective. By the end of the course, a student will be able to explain concept and terminology of digital electronics, the application of logic to design, creating and solving problems using gates, use of De Morgan's theorem to simplify expression, formulas and empirical map to reduce Boolean expressions, and logic circuits to the simplest form. Create circuit to solve problems using gates to replicable logic functions. Design an evaluative solution to a digital design problem. The last one is design and implement conventional logic circuit using reprogrammable logic circuits. The course material. Couple of textbooks, their authors, and the editions is given here. We will recommend which chapter will follow from which book, and you can double check with the textbook as well. Learning outcome of this lecture. After completing this chapter, you will be able to describe the functional operation of a basic logic gate using truth table, logic expressions, and logic waveforms. Describe the meaning of a logic family and the operation of the most common technology used today. Determine the operating condition of a logic circuit and driving various types of flows. Implementing circuits from Boolean expressions. It's important to understand the Boolean algebra. Boolean algebra covers the operations that we can do with zeros and ones. They are basic building blocks for computation inside digital device. It is a means for expressing relationship between a logic circuit's input and output. Letter symbol might be used to represent circuit's input and output. For example, the letter A might represent a certain digital circuit's input or output, where we must have either A equals 0 or A equals 1. The Boolean 0 and 1 don't represent actual numbers, but instead represent the state of voltage variable called logic level. The voltage in a digital circuit is said to be at the logic 0 level or the logic 1 level, depending on actual numerical values. Boolean value 0 might be assigned to any voltage in the range of 0 to 1.2 volt, and 1 might be assigned to any voltage in the range of 3.2 to 5 volt. Boolean algebras. In digital logic, several other terms are used to represent 0 and 1. So the example of these are for logic 0, if you can write it as false, off, low, no, or open switch. For logic 1, you can write it as true, on, high, yes, or close switch. It's important to understand the concept of buffer. So this is the first basic gate. The output of a buffer is simply the input. The logic symbol, truth table, logic function, and logic waveform from the buffer are given in the following figure. So this is a symbol of a buffer at the left, and after that you can see the truth table. So whatever the input is, that is following the output. So input 0 will be followed in the output 0, input 1 will be followed in the output 1. This is the typical waveform. So this is the input waveform. This is called timing diagram as well, and this is called output waveform. So we are giving 0 as the input here, and we are getting output 0 here. So we are giving 1 here and getting output 1 here, just following the input. Logic operation. There are only 3 basic operations: OR, AND, and NOT. Digital logic circuit called logic gates can be constructed from diodes, transistors, and resistors connected such that the circuit output is the result of a basic logic operation performed on the input. Truth table. The truth table is a means for describing how a logic circuit's output depends on the logic level present at the circuit's input. The table of two input logic circuits are given here. So this is our input A and B, and this is our output. So altogether, this representation is called the truth table. The number of input combination will be equal to 2 to the power n for an n input truth table. The list of all possible combinations follows the binary counting sequence. For example, how many table entries are needed for a 5 input circuit? So it is 2 to the power n. Input is 5, so n equals 5, so 2 to the power 5 equals 32. So 32 table entries are needed. OR operation. So OR operation OR gate. An example of such is a kitchen oven. The light inside the oven should be turned on. So for that, we have two conditions, like condition A and condition B. If the oven light is switched on, a separate switch to turn on the interval light, or condition B, if the oven door is open. If either of these conditions is true, then the light inside the oven should turn on. A and B are combined using OR operation to produce the output X. Here X represents the light is on. The output X is logic 1 for every combination of the input. Condition A and B, where one or more inputs are 1. The only case where X is 0 is when both the inputs are 0. Note, for both conditions, main power switch has to be on. This is a typical example of OR operation. The OR operation produces a result of 1 whenever any input is 1, otherwise the output is 0. OR gate is logic circuit performs an OR operation on the circuit's input. The expression of such example is x equals a plus b, which read as x equals a or b. It's not really plus. In logic circuit is called OR. X equals a or b. OR operation. So we have the truth table here. So this is A and B, that means we have two input, and we have X, which is the output. This is the symbol of the OR operation. So we have A and B, and as output we have A or B, not the plus. So X equals A or B. The plus sign doesn't stand for original addition, it stands for OR operation. OR gate output from timing diagram. So consider we have a gate something like that. We have two input and we need to determine the output waveform. So your two input waveform are given. So A is your input, B is your also input. So these two input is given. So you need to determine this output. It should be the output waveform for this one. Okay, so for such, let's check the output. We need to remember the truth table for our operation. Then it will be easier to understand what's going on here. So say like we have divided couple of intervals at t0 to t7. So up to t0 to t1, just check here. So t0 to t1, both of the input is 0. If both of the input is 0, then output is also 0. So output follows the input. And here, from these values to these values, this is T1 to T2. In T1 to T2, our input is A1, A is high, B is low. So from the truth table, we know if either of the input is high, the output will be high. So that's why the output from T1 to T2 is high. Next, go to T2 to T3. So for T2 to T3, we have input A is high, input B is high. So if as both of them are high, so output will be also high. So this also follows high. Next, go to T3 to T4. So here A is low, B is high. Again, the output will be high. So for this one, T4 to T5. So our A is 0, B is 0, output will be 0. Both of them is 0. Let's go to the T5 to T6. Our A is high, B is 0, so output will be high. And for the last one, T6 to T7, our A is high, B is high, so our output will be high. If you are still unsure how you can determine this, I suggest to check again the truth table. So just here, if both of the inputs are same, then it's 0, or it could be 1 as well. The main thing is here, if either of the input is 1 or both of the input is 1, then output is 1, otherwise 0. Let's go to the next session, a glitch in the output. A glitch is an electrical pulse of short duration that is usually the result of a fault or design error, particularly in digital circuits. For example, many electronic components such as flip-flop are triggered by a pulse that must not be shorter than a specific minimum duration. Otherwise, the component may malfunction. A pulse shorter than the specified minimum is called a glitch. It is a short-lived fault in a system, such as a transient fault that corrects itself, making it difficult to troubleshoot. So, we'll try to understand the concept of glitch and how it is occurring here. So, just consider you have the two input initially, the timing diagram of two input. Just consider we have A and B. We will consider C at the next slide. So for A and B, just try to determine the output first. So if you look at timing T1, so you can see at T1 our A is going from high to low and our B is going from low to high. So glitch may occur when both the inputs are changing their state at a time. Like both of the input, like A is changing from high to low, B is changing from low to high. So both of the inputs are changing at the same time. In this case, glitch occurs at time T1. So due to this T1, glitch is occurring when A is going for high to low and B is going for low to high. Now consider a situation for the glitch example we discussed before. So what would happen to the glitch in the output if the input C sat in high state while A and B are changing at time T1? I suggest you try to find the solution for that. If not, we'll discuss it in the next lecture. Thank you.